All right, well, welcome. We'll go ahead and start with the next speaker here. It's a little bit ahead of schedule, but that will give us a little bit more time for the presenter and for questions afterwards here. So very pleased to introduce you to Jason Vranek, who is the CTO and co-founder of Pufferfi, and you're going to be talking about native liquid restaking.
Yep. Awesome. Yeah, thank you so much for having me here. So I'm going to talk a little bit about Puffer, some of what was our journey to get here. So we'll kick it right off. So Puffer is a native liquid restaking protocol. There's sort of a lot of new words in there, so I'm going to give some background first. And yeah, let's get started. So I'm sure all of you are probably familiar with liquid staking tokens, but for the rest of the audience maybe watching, I'll try and give a quick background to really see how this contrasts with what we're doing at Puffer. So for recap, pretty simple. Stakers deposit ETH, they mint some kind of liquid staking token, and nodes are able to borrow this ETH to run validators to generate proof of stake rewards. They earn a portion of the rewards, and the rest goes back to the liquid staking token holders. And the idea is that these stakers can redeem ETH plus rewards minus any penalties accrued by these validators at the future. So there's some pros and cons here. I think the industry is really leaning towards pros because of the yield of LSTs, the ease of use, the liquidity, the ability to take it to DeFi, but also from the node operator point of view, there's this increased capital efficiency. You don't need 32 ETH to run a validator. But of course, there's the cons. As we saw from Mike's talk at the beginning, we have proof of stake congestion. We have centralization vectors where proof of stake, the validator set is kind of starting to get dominated by some protocols, and really reduced economic security when we're talking about permissioned liquid staking protocols where the actual node operators aren't putting down collateral. So while the industry today might be leaning towards the pros, I think really we should be focusing on tomorrow's problems because they might be sort of worse than the benefits we're getting today. And so this was really how our journey started, but we're also coming from an out-of-protocol solution. So you might know Puffer a little bit from our first sort of intro. We built this thing called Secure Signer. It's this anti-slashing kind of mechanism, and actually Ladislas will be giving a talk on this in more depth later today. So I'll just kind of cover it at a very, very high level. But the idea is that you have what's called a secure enclave. In the current implementation, we're using Intel SGX as a trusted execution environment. And the idea is we're going to expand this to other hardware manufacturers. And what you do is you really generate your validator key and store it within this secure enclave. And as the actual validator, I have no idea what my actual validator private key is. And this is important because it really prevents me from shooting myself in the foot. I'm not going to accidentally be running a validator on two separate clients and get slashed because I don't have the ability to really take my key and put it in multiple places. And these enclaves are pretty interesting because you're able to actually add logic within them. And what we're doing is we're adding these anti-slashing rules, very similar to what your normal validator clients and consensus clients are already doing. But it's just considered a strict security enhancement because the actual logic is within this tamper-proof environment. And so we built this as part of an EF grant and open sourced it. So while we use it within our protocol, it's also available for solo stakers as well. And I think that's part of Ladislas's talk is on how solo stakers can really be using this. So this was our approach, and when we came into building Puffer, and the idea was, okay, we can reduce slashing risk, and for a permissionless liquid staking protocol, this really means we can reduce the bond requirement, which would help more validators really be able to participate, and that helps increase decentralization. And the end, did we solve this, or is this too simple? And so Puffer has really come a long way since that. Definitely this enclave and secure signer is a big part of our protocol, but we've kind of come a long way since then. So where are we today? So we in building this protocol, really wanted to follow some guiding principles here. So the main one is we have to be permissionless from day one and always. And the protocol should be safe. And this always, of course, for stakers, like the people holding the LST, but also for the node operators. So this is where technology like Secure Signer comes in. Eventually that can be complemented with DVT as well. And then it should be capital efficient. It should be accessible for node operators to be able to participate. And it should be profitable for those node operators, for people to actually have the incentive to go and run. And of course, scalability. If your protocol isn't scalable, then you're not going to be able to attract enough capital to grow and really onboard more validators as well. And finally, ethos alignment, maybe most important here, is that the pool should really be self-capped and try its best to follow along with the ethos of the community. So, okay, with that being said, following those guiding principles, really what is Puffer at a high level? So we're Ethereum liquid staking, where you earn proof of stake rewards with your validators, but we're also doing native restaking on top of Eigenlayer. So that's able to generate restaking rewards. And maybe a quick clarification here, because I think this is often lost, is there's a difference between native restaking and kind of regular restaking. Whereas regular restaking is like you take your liquid staking token and you restake that to run some of these Eigenlayer AVSs. With native restaking, you're taking your Ethereum validator, their beacon chain ETH, and then restaking that to run different applications. So what does this result in? So Puffer, we're calling this native liquid restaking, and instead of a liquid staking token, we're calling this a native liquid restaking token. So that's kind of the overview. So what are some of the features? So one thing we put out last week was a post that we collabed with Justin Drake on called Smoothing Commitments. And the idea is kind of very simple, but also kind of interesting. And I think it opens a lot of potential research as an out-of-protocol kind of technique we can use. So the idea is that if I want to run a validator for a certain number of months, I can actually pay upfront some close to the expected value of what I would make as a validator. And in exchange, I get to actually keep all of the rewards that I generated. So all of the consensus rewards, all of the MEV. And this really has a lot of interesting kind of results. So one of them is from the point of view of stakers, like on Puffer, they actually earn months of rewards upfront rather than over the course of many months. And so this has some nice growth properties for like an upcoming liquid staking protocol to try and compete with these more centralized ones. And another important thing is, I think Justin coined the phrase rug pooling, the idea where if your validator's collateral is really low, then there's actually clear incentive for you to try and steal MEV if you get this juicy block that's worth more than your collateral. And actually trying to police that and enforce that is like probably an unsolvable problem unless we have some kind of enshrined solution like MEV smoothing or MEV burn. And so yeah, you feel free to check out at the bottom, there's a link to the research post. And so what does this look like now to become a node in Puffer? So there's kind of two flavors here. If you're using Secure Signer and you're able to prove it, and we built these smart contracts that allow you to be able to prove that you're running the specific enclave, then your bond is lower, and so you'd be paying, locking 1 ETH collateral, and then paying this smoothing commitment for whichever duration you prefer. But if you don't want to actually use the hardware or if you're having difficulty getting access to it or you want to run it on your existing setup, then it would be a slightly higher bond. So, okay, how does this all come together in Puffer's actual architecture? So we have these things which we're calling strategies. You can also think of them like restaking modules. So the idea is that a node would deposit their bond into the Puffer protocol. And sort of the main thing here is that we have this non-restaking kind of module as like the most big one. Like we don't want to we want to diversify in how all of the ETH is distributed within the protocol, and prioritizing the non-restaking is sort of the least risky. So Then what happens is, so the node, after they deposit, they're going to borrow ETH to run their validator, and they're going to deploy that into the strategy of their choice. So for example, that could be a strategy that runs EigenDA. It could be one that runs like the mock alt layer stuff that we just saw from the last presentation, or any new AVSs that come to market and combinations of them. But one important thing is that the actual strategy should be immutable in the actual AVSs that it commits to, so that it's not just adding new ones that could cause slashing. And so how is this broken down? So each of these strategies will have many different validators deployed into them, but they'll be run by one strategy operator. So what this looks like is the strategy operator is the person that's actually running the AVSs, but then part of the rewards are trickling back down to these validators that are within the strategy, and also down to the LST holders as well. So what this really looks like from the point of view of a node operator is I can deploy a validator for like much less capital into one of these strategies, and now I'm able to also earn restaking rewards on top of my proof of stake rewards, and so increase the viability and the profitability of my validator. So what is, so Puff Eth is our native liquid restaking token, or our liquid staking token, and it is a combination of these restaking rewards, these smoothing commitments paid by the validators, and also the staked ETH deposited by the stakers. So maybe let's try and recap real quick. So stakers are going to deposit ETH, and these nodes are going to pay smoothing commitments and deposit bonds. They're going to then give a month's worth of proof of stake rewards upfront to these stakers through the smoothing commitments. And the node is then able to borrow 32 ETH to deploy it to the strategy of their choice. And this ETH will be natively restaked and then run by one of these strategy operators. And this will in turn generate restaking rewards that sort of flow back through the protocol and pay back the validators and stakers. So there's some interesting dynamics when we're talking about these smoothing commitments and these like high upfront payments from the node operators. So we're calling these things growth spurts. So one way to think about it is that whenever a node joins Puffer now, the actual yield on the native liquid restaking token will increase. So from day one, this might start as like just 1-to-1. You have 1 ETH is worth 1 Puff ETH. But then because of this high growth dynamic, like very quickly you can see how like the conversion rate can really grow. And I think this is very kind of interesting. Mike had also talked about the churn limit that's being introduced in one of the future EIPs. And from the point of view of Puffer, like we're trying to compete with some of these centralized liquid staking protocols, but the churn limit also sort of slows our growth as well. But it's interesting because through this dynamic, we're actually able to get some bootstrapping and growth of our protocol before the validators even hit the validator set. So that's where the growth spurts come in. But of course, in ethos alignment, we have what's called our burst threshold. So once we hit that 22% threshold, the protocol will automatically hike up the fees and sort of economically like reduce the incentives for you to join as a Puffer node. Yeah, so let's maybe wrap this up and highlight some things about Puffer. So we tried to sort of go back and see if we reach some of these guiding principles. And so for safety, we're having our anti-slasher. We built it with SGX, but we're starting to diversify that into multiple different hardware manufacturers. And of course, like all of our nodes are bonded to prevent or to sort of align things better, and also because we're permissionless. And then for the viability of these node operators and the growth of the protocol, we're combining these proof of stake rewards and the restaking rewards as well. And of course, yeah, for ethos alignment, we're capping the protocol to 22%. So with that, yeah, thank you so much. And I'm yeah, happy to take any questions. And yeah, please, these are some of our links. We're going to actually be launching on the public testnet this month. So yeah, please join, run some Puffer nodes. But thank you.
We have time for multiple questions. Does anybody have any questions for Jason?
Hey, Jason, great talk. So I have a quick question. When you run the sort of the SGX, is there any sort of major latency compared to the nodes without SGX? Just want to know some of the data.
Yeah, actually, yeah, very, very low overhead. And also in the implementation, if you're familiar with Web3 Signer built from Consensus, Secure Signer is actually just like a re-implementation of that in Rust. So in Rust, like nice and fast, and yeah, there's little latency.
I see. Sounds good. Another question, can you roll back to the slides with the loop?
Yes.
Yeah, this one. So I'm curious about which component in the future you would like to apply the SGX in? Will it be on the node side and also the operators, and so what are the components you will have with the SGX?
Yeah, great question. So primarily right now, that's starting on the node operator side. So when you're actually registering your node, you're actually going through this process of remote attestation where you're proving that you're running this specific enclave that's running this specific set of software. And really what this is showing is you generated the key inside of the enclave, and the enclave is running all the necessary / protection logic. And yeah, you're able to prove on chain that you're running that and get accepted into the protocol. So that's where it's used today. And we're going to expand that to other hardware manufacturers. But actually moving forward, I think there's a lot of interesting applications of that, especially in the context of eigenlayer. So we're doing this for Ethereum proof of stake to prevent equivocation from our nodes. And equivocation is one of the things in many of these ABSs. And so you can actually reapply that same technology and have so from our strategy operators' point of view, if they're running another consensus protocol through eigenlayer, they would be able to use SGX as well and prove that they're running that as well.
Any other questions from the audience here? I had one for you, Jason, maybe two. The first one is with regards to storing the signing key, the validator key, and the SGX enclave in there. What are the risks, not being very familiar about that system, but is there a risk of maybe that node getting damaged or destroyed and then losing the key? Is there a way to back it up on steel or in some other secure system?
Yeah, so that is definitely one of the trade-offs, is that if your hardware is just obliterated, the idea is that it's only on that physical machine. So you won't be able to recover it in that case. So we really recommend pre-signing these exit messages in advance. So you'd have to withdraw in that case, but also post EIP 7002, you'd also be able to do that through the smart contract.
Yeah, that was one of the thoughts I had. And then second follow-up question is with regards to the comments you had on the MEV theft, the stealing of the MEV. What is the approach or solution that you're taking now to ensure that your nodes that are bonded with the 1 ETH or 2 ETH are indeed sending that MEV to the correct fee recipient?
Yeah. So that is kind of the hard problem, is how do you enforce that? So you can use these off-chain solutions, using an oracle to check okay, if our validator produced a block and the fee recipient is incorrect, then we can go and slash their bond. But really this is a difficult problem because one, now we're introducing this extra dependency on an oracle. Maybe once 4788 comes out, we can do that more trustlessly. But I think the major issue here is that we don't know if there's off-chain deals going on where maybe just pennies of the MEV is actually sent to the fee recipient and the rest is done off-chain. So this is where real in-protocol things like MEV Bur would help that. But the idea with the smoothing commitments is, from the point of view of our protocol, we don't care anymore if you're keeping all of the MEV, because the idea is that you paid up front close to the expected value of it, so that now fee recipient goes to your own wallet, and that's fine.
Okay, excellent, excellent. So that's part of the MEV commitment smoothing is actually an upfront cost, and then the node operator gets to keep the MEV.
Yeah, exactly.
Okay, excellent. Any other questions from the group before we let Jason go? All right, well, thank you very much.
So thank you.